Okay, so thank you. My name is Hugo and I work at KSAT. I'm a project manager. I'll talk about SAR and give a brief introduction. There's a lot of slides, and a lot of information, but I only have 15 minutes, so I will not go thoroughly through everything, but you will have the presentations available so you can have it for reference, for future reference. So SAR is an active sensor. It emits energy sideways, and the energy from the Earth is reflected back to the sensor in different levels. So SAR does not need light to image, and it looks through clouds. I will go through some of the parameters users should take into consideration when ordering SAR data. So we will look at wavelengths, a little bit about imaging modes, briefly on polarization, incidence angle, product level, and show some examples. So SAR satellites has been around since 1979 or 78. This is the first SAR satellite, CSAT, made by NASA. And this is an image of Oslo Fjord from October 1978. The SAR satellites move in a dusk-dawn orbit. Because the sensor is active, it needs energy. So the traditional orbit is the dusk-dawn orbit. And this is the orbit you see here crossing the pole. And this orbit gives acquisition times in the morning and in the afternoon, locally, all through the globe. When we are high north or in the south of the globe, we have access to more satellite data because all the orbits meet at the poles. As SAR does not need light and it looks through clouds, it's a perfect sensor for operational, reliable monitoring services, since we can plan an acquisition and be quite confident to receive the image as promised. And at KSAT, we have our in-house processors and our global antenna network, and we use this to get the information quickly to the processor and to deliver services fast. So we have operational services for oil spill detection, vessel detection. We provide ice object information, and we are also a reseller of multi-mission data, both SAR and optical. Today we have a toolbox of more than 20 satellites for SAR, where we have in-house processors for all of them except for ISI, which uses cloud processing. And this means that we can deliver a service 1 hour after acquisition or 2 hours after acquisition. So the SAR satellite, the sensor emits energy and some is reflected back. Here's an example of how we detect oil spill. We have a little bit wind on the sea surface. And you see the SAR image in the bottom of this slide. And the sea surface is gray. And that's because you have a little bit of capillary waves reflecting some of the energy from the sensor. An oil spill will dampen these capillary waves, and the surface will be slick like a mirror, and the energy doesn't come back to the sensor, and we have a dark part of the SAR image. The best reflection you will get from vessels or installations where you have a double reflection. So you see example on the right here, and targets here will really light up, and you see the white dots in the image down to the right here. Things to take into considerations when choosing a sensor is which frequency do you need. So the SAR is in the microwave part of the electromagnetic spectrum. X-band is available on TerraSAR and Cosmos SkyMed and on ISI. It gives a high resolution and a low penetration. C-band, many know from Sentinel and from RadarSat, is very much used. A little bit more penetration, quite good resolution. L-band is also available on a few satellites. ALOS is one of them. We have more penetration and the coarser resolution. And here are the differences with vegetation, where you in X-band only see the leaves, and you penetrate more and have more biomass on the L-band. The same on the bottom here on a glacier, you can use X-band to have some information about the top snow layer. The C-band penetrates a little bit more, and the L-band can say something more about the ice conditions. A SAR satellite can image with different imaging modes, and the scanner mode is the coarsest resolution and the widest SWOT. Strip map is a single strip, often with 3 meters resolution and around 40 kilometers wide. The spotlight mode is the highest resolution, where you can image with 50 centimeter resolution or 1 meter resolution, but you have a really small image. There's a table you can look at afterwards if you want to. Here's an example of how the different SWOTs look like. So the spotlight with highest resolution is really small. You can't use it to get an overview. You need wider SWOTs for that. So you need to choose your SWOTs. You can also have information about how you process and the image products you choose. So there are 4 or 5 different image products, which are the normal ones. And the single look product is the highest resolution, used for SAR interferometry and for polarimetry. But it's not easy to look at, and it's the mode you or the image product you use for science. If you want to look at images in a GS tool, detected products are better because they are multi-looked to reduce speckle, so you get less noise, but the resolution is the cost here. You lose a little bit on the resolution. And you have to decide if you want the image in a map projection or in a ground range projection. And there's a possibility to, if you are in if you are onshore and you have elevation differences in your image, it's a good idea to get an ellipsoid corrected product using a DEM, so the image is auto-rectified and the pixels are precisely located in the image. Here's an example of different resolutions, and here we see the sea ice north of Bjørnøya. The first image here is a 500 kilometer wide radar sensor wide, 100 meter spatial resolution. We look at the TerraSAR image with 18 meter spatial resolution here. It's 100 kilometers wide spot. And a 5 meter resolution Cosmos SkyMed strip map image. If we zoom in, we see more information. We can go even further here. And we find ice objects at 5 meter resolution in this product. In the 18 meter product, you don't see the 5 meter product, the 5 meter objects anymore. You can see objects around the 18 meters as the resolution of the image. And in the RadarSat 100 meter resolution, you don't have any information anymore about these objects. Another example is coherence imaging, where you use the same geometry and you image with the same from the same incidence angle and the same image geometry. And we can use this, so everything is constant except the moving parts here. So we can easily see changes. Where this is from Greenland, where icebergs drift. So the glaciers are calving and you see ice moving around here. Like this. This is my last slide. It's where you can find more information about SAR and the different image products. That's it from me. Thank you.
Okay, thank you very much for the invitation, and my talk kind of follows on very nicely from Hugo's, as you might imagine, because there are some similar considerations, but also some very different considerations when it comes to optical satellite data, and particularly with kind of challenges in terms of the nature of optical data versus SAR when it comes to Arctic. So we'll touch on some of those. Similar to Hugo, I have a number of different examples and different things to talk through that hopefully spark some questions. It won't cover everything, but hopefully it provides a good starting point for people who are interested to learn a little bit more. So I first wanted to touch on really the difference between optical and radar. For some of you, this may be very obvious, but for others who are maybe less familiar with working with these different data sets, optical does rely on the sun, so very different to SAR in that perspective. So it does mean that images collected with optical are affected by clouds and other atmospheric conditions. So this is an area, this is actually in the tropics, but the same would apply anywhere where there is clouds. And if we look at a radar image of exactly the same area, we don't have that same impact. So the point really of showing this slide is that in some cases, there may be an argument where radar is the better solution to meet a specific need, but it could be that there is an opportunity to combine the nature of the radar detections, which are more textural focused, as well as the optical, which are looking more at color differences. And those features don't necessarily come exclusively, they can also be used together. So just similar to Hugo, a little bit of the fundamentals of optical remote sensing for those who are less familiar, but I suspect many of you will be perhaps more familiar with optical imaging than maybe you are with SAR. Optical imaging relies on the sun, so it's only daytime imaging. I will caveat that with that there are nighttime imaging options, which are more looking at say nighttime light activities, gas flaring at nighttime, but really for the operational remote sensing activities, I believe most of you will be much more familiar with the daytime imaging, which is really 95+% of the activities in optical remote sensing. So with the sun and the reflections that then the satellite is seeing, so this is a passive satellite system, it's not active in the same way, so we're receiving that signal based on reflectance from the Earth, but that reflectance comes in a wider range across the electromagnetic spectrum, and we'll talk about what that means and what parts we can actually see. Most of the satellites that are optical are sun synchronous. That means that they're relative to the sun for this reason, because they rely on the sun to be able to see the features. And most of those are polar orbiting, which obviously becomes important when we're talking about Arctic research, because as Hugo says, the same with the SAR, with most of those orbits going over the poles, that does increase the number of image captures that are available. But there are now other opportunities with different collection modes that we'll touch on. They will be less relevant to the Arctic region, but we'll touch on those for awareness as well. Firstly, and similar to Hugo, I wanted to talk about spatial resolution, because that becomes important when we're talking about the types of features that we might want to see. It's a little bit different to SAR, where a pixel to pixel in optical is more defined for the feature that you want to see, rather than in SAR, which is reliant on a backscatter response, where the feature may be much smaller than the pixel size allows. With optical, it's very similar to aerial photography, where those features will be more visible to see and therefore a bit more obvious. So I just quickly put together a graphic that kind of shows from the low spatial resolution, so 30 meters downwards, just to see the different types of features that we can see over this same area, and just to give an indication of really what that means, because low resolution doesn't mean it's not useful. It's useful for the applications for which it's applied, and vice versa. High resolution has a lot of advantages, but may not necessarily be needed for all applications. So if we go from 30 meters and we start kind of stepping up the resolution range down to 10 meters, we're already starting to see some more features here. We start to see what looks like some linear features. Maybe there's something going on in the middle. We can't quite define that at this stage. If we go step down again to 5 meters, okay, we can see a lot more clearly. We can see there's some roads, there's possibly a settlement or something in the bottom left of the screen. And this could be a mine area. We're seeing a kind of stepped feature in the center of the screen, which could be indicative of that. So we're seeing some detail, but not vast amounts of detail. And if we take this down, in this case, to 50 centimeters, but we could go down to 30 centimeters, which is the highest spatial resolution currently offered by optical satellites, then we can indeed see this in a much more detail. Now, we're not very highly zoomed in here. Obviously, if we were, we'd be able to see the features in much higher clarity at 50 centimeters. But really, the point of this slide is to show the range of different spatial resolution and how that can be a consideration to the type of activity you have and what you're trying to achieve. And we'll talk a little bit more about that a little bit later on. But whilst we're talking about spatial resolution, it's also important to talk about spectral resolution. So what can we actually see, not just spatially, but the features that we can see and how can we discriminate those different features. So this is a nice example from Digital Globe, which is now Maxar, where they put this nice graph together for when they launched their WorldView 3 satellite a few years ago. But I think it's just a really nice example of how the Planck curve for reflectance relates to what we can see naturally with our eyes. So you can see the nice eye icon on the image here, which is the visible portion of the electromagnetic spectrum, and that's what we can see naturally. So everything outside of that is not something we will naturally be able to see, but we can have an optical satellite that includes spectral bands or spectral capabilities in those portions of the spectrum, and suddenly we can enhance features that we would never naturally be able to see with our eyes. So this concept of spectral resolution is something I thought I'd put together an example in just a second that highlights what I really mean by that and what advantage that can have, because that can be important to different types of applications. And this is just another example to show, in this case, spectral responses. So every feature on the ground looks different. And that the reason it looks different is because it reacts different to the light. So we will see a different pattern of response for, say, vegetation versus iron oxides. And as you see, clay materials, all these features look different. And we can, with the right targeted spectral bands or channels of information, we can start to separate those features from each other and therefore get a different understanding. And all of this will really depend on what the application is and how much value that spectral component is. The majority of satellites will, as a minimum, have 4 spectral bands. So that's the visible red, green, and blue that we're all familiar with, and a near infrared band, which covers this really high peak you see in the vegetation. So very good for environmental general land mapping. The combination of those 4 works very well. But if you're looking to do more analysis, then we're going down this area outside of our visible domain, and we see satellites like Landsat, Sentinel. The publicly available satellites have some capability here, but also other satellites, WorldView 3 being one of those, that have these additional capabilities, allowing us to separate some different features than what we can see naturally. So I just put together a visual example of this just to give some indication. This is an area in Australia in this case, but the same concept applies regardless of where you would do this. So this is a natural color image. So similar, think of it like we would see in Google Earth. Green in essence would be vegetation in this case. The lighter area is more exposed and more sandy in this area, given that we're in a drier part of Australia. If we change the input color channels into that visualization, then we can see some red over on this side. So this we've changed this so that we could highlight vegetation. So we see some red over this side. We're seeing some red in the river channels. I'm hoping you can see my cursor, but hopefully, if not, my description is helping. And we're seeing some other colors on some of the other geological features in this case. But again, as I say, this could also be used for different types of landscapes, and there are different ways we can modify that color for different types of features. And finally, just another different color representation. Again, we're still using 3 input bands, but they are outside of what we can see naturally. So we're able to pick out different features. And this can be really helpful for separating different types of surface type, different types of geology, different types of vegetation and land cover. So a very nice tool that from a visual perspective can be very helpful. And that's, of course, before we do any other classifications. But really, finding the right imagery is also part of the challenge. And that's something we do quite a lot of at KSAT, and is to help people understand the differences between the imagery that's available and also what might be most suitable for different applications. So on the left-hand side, you see a lower spatial resolution image. So lower spatial resolution images cover larger areas, and they tend to be lower cost, but also less detail, lower spatial resolution. As we move to the right-hand side, You've got higher spatial resolution. So this is where we're 1 meter or better. They're higher cost and they cover much, much smaller areas. So there's those kind of considerations when it comes to what data might be most suitable. And also you may be interested in the time of day of collection. As we talked about, the images are sun synchronous, and most of those collections are in the morning. However, there are collections that happen around lunchtime in the Arctic area as well. So time of day may be important. The spectral capabilities, as we just talked about, may be important. The need perhaps for stereo imaging, if you're looking to do 3D visualization, may be important, as that's not available with every satellite. And also viewing angle, how steep off nadir, off straight down will be suitable for your application, and also how quickly you might need the data. KSAT has near real-time processors similar to what we have for SAR for 2 optical high-resolution missions, and many of the other missions also provide data quite quickly, but that could also be something that might impact what data might be most suitable. And when we talk about coverage, this example, similar to what Hugo was showing, just kind of indicates what we're talking about here. So the blue outline here is a Landsat image, covers a vast area, and it's about 185 kilometer swath, covering an area that's nominally just over 34,000 square kilometers. If we look at ASTA or indeed SPOT, both have a similar 60 kilometer swath, and that covers about 3,600 square kilometers. And then down to the smallest, which is the highest spatial resolution, which would be anything sub 1 meter, something like KSAT or SkySat or any of the SAR satellites. They're around 12 kilometer swath, but they only cover then 144 square kilometers. So really what you're trying to do and the extent of your area will have a bearing on what may be the most suitable data. I very briefly wanted to talk about some of the examples. This is a very much a non-exhaustive list of data that's available, but just something, if you're less familiar, maybe some of these names will be names you've come across, some perhaps not, but just to touch on a couple of those and some examples before we close. So the image on the right here is the coverage of Landsat. It's collecting every 16 days, but now every 8 days since the launch of Landsat 9. And this is collecting all the time. You don't task this satellite, it's always collecting. And similar to ASTA, it doesn't have a direct repeat orbit, but it's collecting mostly on a background mission and has some targeted collections. But all of those 4 top satellites there, they're all public missions many of you will be already familiar with. The bottom set there still fit within this low to medium spatial resolution range of above 5 meter spatial resolution, and they cover different types of satellites. So some of them are 4-band imaging satellites, so the similar 4 bands we've been talking about. GHGSat is a methane or emissions detection satellite. There are 2 hyperspectral satellites there, Prisma and NMAP. And some of these systems collect in very, very wide swaths, but they are all commercial systems. So a different type of solution than some you may be familiar with, that could still be advantageous to your applications. And then when it comes to high and to very high spatial resolution, so anything below 5 meters, and I know we have someone from Planet here, Rhodri, so I won't talk too much about Planet data, but obviously Planet's offerings, both through PlanetScope, SkySat, and also the archive of RapidEye would be relevant when we're talking about this spatial resolution range, as well as a whole wealth of other data sets. And these, as I say, are just a selection of what's here now, and also what's coming in the next kind of 6 to 12 months. And we talked a little bit about kind of orbital repeat and revisit. Being in the Arctic, this is actually very advantageous. It means the opportunities are much, much higher. But the challenges, of course, will be the time of year of collection, because when it comes to the darker period in the north, it's very, very challenging. We can't get that data, and also when we're getting close to that period, the sun elevation angles can be so poor that it can be very difficult to get a good image. So the actual nominal imaging time in the very high Arctic could be quite small. That being said, there's still quite a lot of data that's collected, quite a lot of data that's in archive from a number of these satellites. So depending on your area of research, there could already be some good sources of data existing. And just some considerations with this data. I know we've talked about some of these, but just to kind of visually show what this looks like. I mentioned about viewing angle. So lots of images are straight down, but invariably they are not quite directly straight down. They're a little bit off to either side. These satellites are quite agile, particularly the very high resolution systems that are collecting very flexibly lots of different collections. So the example here on the left shows a quite steep viewing angle over this area in Rome. Now that's could be very nice, very suitable for the application, but it can be very challenging for mapping. It could be very difficult because it reduces the quality of the image. You won't have that native 50 centimeters the further you go away from a native viewing collection. So these are kind of things that you might want to think about, the impact of whether a steep collection could be okay for your application. The advantage can be that in cloudy areas or areas where there's lots of haze, for example, as you see on the image on the right, if you have a wider collection angle, that gives many more opportunities and more flexibility with the collection, which could actually be very useful in those kind of areas. But then it comes with these other considerations as well. Haze, as I say, and clouds, as we've talked about, will be a challenge. And actually, on this next slide here, the other challenge I think we have in the Arctic is, of course, snow and cloud looks quite similar. They're both white, and sometimes it's quite difficult to separate the two when the satellite operators are monitoring the extent of cloud cover in an area of an image and classifying that. It can be quite difficult to do that in the Arctic areas. So the image on the left is from Devon Island. And you can see there is definitely some snow here. We can see some of the kind of crevasse and lake features in the image under the cloud, and then there's some popcorn cloud here as well. So there could still be information here, but kind of understanding that there could be some challenges in those types of areas is important. And likewise, the image on the right, which is in northern Greenland, this is a mosaic of some spot data. There's some cloud right in the center. Wasn't immediately obvious when looking at the thumbnail of the image prior to ordering the data. In this case, it doesn't have a significant impact on the analysis, but it's just something to consider, particularly if that cloud happens to be in an area that might be of interest to you. And just wrapping up very quickly, finding really the right imagery is really important, but the main thing is what the question is. What question are you trying to answer? Because that really dictates what might be the most suitable imagery rather than the other way around. So it's always something to keep in mind. What question you're trying to answer, the more information you're able to share on that, the easier it is to help find the most suitable imagery. And just some nice, pretty examples, I think, to close with, different types of applications. Not all of these are perhaps relevant to the Arctic, but I think in general, it's just nice to see some other examples. Obviously, DEM or 3D visualizations are something that are relevant regardless. They actually work quite nicely over snow areas if the snow cover is reasonably stable. For example, if there's been a long period of not too much new snow, you can still get some really nice elevation products. The GIF that you see running there is looking at some changes over a period of about 6 weeks over some of these crevasse areas in Devon Island, and showing the changes that we're seeing over that area this summer. But there's also change detection. The image on the right there shows some change detection, which could be applied to any type of area, and also, of course, feature extraction. So there's lots of different things that you can do with this data. And this is just a nice example that we had from a couple of years ago, supporting some situational awareness. This is we were notified of a trawler becoming stuck in the ice, and asked to help support with some imagery that could help the rescue efforts try to get to this trawler. So this was the North Guider incident in June 2019. So we got some high spatial resolution data. And in this case, it's within the red box on the left-hand side. You can see on the right what it actually looked like. You can see the boat, in this case, on its side. And imagery like this, as well as some of the ground information, helped to rescue this vessel. And vessel, of course, is a great application of optical data, similar to what Hugo was saying as well. It provides a little bit different detail when it comes from comparing from optical to SAR. And so I just wanted to wrap up, I think, on that point, and just kind of reiterate that the question that you're trying to answer is more important than knowing what satellite to ask for, and also that most satellite data is not collecting all the time. It's very easy to think that is happening, but the majority of satellites are really reactive to requests. So if you have areas that are of interest, it's always good to share those. Those are then areas that can be put to a satellite operator to add to their collection, even without any formal commitment of a tasking, a paid for tasking. And also there may be different options and different recommendations depending on the scale or the budget or all of those types of elements of your specific application, and also different flexible options or ways where you may want to combine different satellites together, and lots of different resources, and we'll leave the slides with you, and of course can follow up on anything in more detail as needed. I'll take it back to you, Sridhar.
So first of all, I wanted to show you like a nice piece of eye candy in this first slide. So this is one of our SkySat images to the 50 centimeter over a location in Svalbard from May last year. But I'll dive straight in. So basically, Planet builds and operates two satellite constellations, one of which is our daily imagery. So that's the PlanetScope Doves. We have about 220 of these, and they captured a 3-meter resolution. So there's no task.
Rhodri, you might want to exchange the presentation mode. I think you have the wrong screen shared right now.
Which one?
This is a demo from Explorer, and I guess you...
Oh, sorry. Okay. My bad. Let me... Is that better?
Yes, that's
okay. Sorry about that. Well, I was hoping if we had a little bit of time at the end to do a small demo, but yeah, let's see what happens at the end. So anyway, we build and operate two satellite constellations. So our PlanetScope Doves, which are the 220 3-meter imaging satellite. So these require no tasking. They're kind of always on, always scanning. And we have the ability to capture virtually the entire world's landmass every single day, or let's say on a near daily basis, taking cloud cover and some orbital gaps into consideration. They capture at an 8-band. So Charlotte was mentioning that most multispectral satellites capture in the RGB and near infrared. We actually have an additional green band, a yellow band, coastal blue, or aerosol blue, known in Sentinel-2, and also red edge. So these allow the users then to do maybe some enhanced indices, such as NDRE, amongst others. And these archive back to 2014. So we do have quite an extensive archive of imagery in our data banks. The second constellation that we operate is called SkySat. And this is our 50 centimeter satellite, so comparable to that of Pleiades and Worldview. So this captures in 4 bands, as well as the panchromatic band. We have the ability to capture on a sub-daily basis, but the difference between SkySat and the Doves, aside from spatial resolution, is that we have the ability it's a tasking satellite. So you have to define the geometry, define the time of interest, and then we'll go capture that image for you. And I'll show a quick video. Hopefully this works. of how we capture the imagery. So as Charlotte mentioned, with most optical satellites, Planet also captures in a sun-synchronous orbit. And this means that the capture times are approximately between 9:30 and 10:30 a.m. Locally, but that means that the sun elevation kind of remains the same throughout the capture cycle. The SkySats are slightly different. So we have 3 blocks of SkySats. The first 2 capture in the sun-synchronous orbit, so the first 15 sats. The sats 16 to 21 actually capture in an inclined plane, which means that we have an ability to capture throughout the day. So not just one capture per day. But as you can see, in the high latitudes, it's actually far easier for us to capture with SkySat because there are more passes, which yeah, for this particular use case is very useful. Oh, let's see if I can go into the next slide. Oh, sorry about that. Why is it not going? Okay, and this is just a little picture of the dove. Not too important. More importantly, here are the spectral bands. So these are the wavelengths versus the spectral response. However, I want to kind of talk a little bit more about the differences in the spectral bands throughout the years. So obviously we've been capturing with the doves since about 2014. And obviously some of these doves have decommissioned, and we have been improving the constellation throughout the years. So the second graphic down, you can see Dove Classic wavelength versus spectral response. We only used to capture in 4 bands. We then improved the radiometry with Dove R, and finally with Super Dove, which now accounts, by the way, for 100% of the fleet, now captures at 8 bands. And we have aligned a number of these bands to the 10-meter bands of Sentinel-2. We understand that this is quite a widely used satellite. So we like to think that Sentinel-2 and Super Doves can be used interoperably. So this slide demonstrates the coverage of PlanetScope from June this year. You'll notice the full coverage is, or we can capture full coverage of Svalbard. But ultimately, the best coverage of data is from about April to August due to the sun elevation. The winter months have this low sun elevation, making it quite difficult to capture optical imagery in those winter months. But yeah, just to reiterate, the current Super Dove orbits extend to about 83 degrees northern latitude. And obviously, I want to put in some shameless eye candy. So this is an example of one of the PlanetScope images over a location in Svalbard from August last year. And this is actually one from August this year. I believe actually this image is either Dove R or Dove Classic, which has now been decommissioned. And the image you're seeing now is a Super Dove, which is the which counts now for the entire fleet of the PlanetScope constellation. So SkySat, I'll dive a little bit deeper into this high resolution constellation. So just to reiterate, we are able to capture any point on Earth at this 50 centimeter resolution, including the high latitudes of the Arctic region, including Svalbard. We can capture at this intraday period. What's quite interesting about SkySat is we don't actually solely capture the images ourselves. We do give customers the opportunity to capture themselves using either our tasking API or tasking dashboard. So if you wanted to capture an image, you had a crazy idea at 3 a.m. and unfortunately none of us are on the phones, yeah, you're more than welcome to actually capture those images yourselves. Our delivery options are quite flexible as well. So we have Planet Explorer, you can see in the middle graphic there, which you probably saw at the beginning of my presentation. So this is a dashboard that basically hosts all of our data. It works a little bit, I guess, like Google Maps, where you can kind of pan around the world, and then you can put in your AOI, coordinates, etc., and it'll show you basically all the data that is available over that particular AOI. However, we also have APIs, and actually the Planet Explorer is powered from our Planet API. Although if you wanted to kind of stay clear from our platform, We also have plugins via WMTS. So we have a plugin for ArcGIS Pro, QGIS. We're working on integrations with Google Earth Engine as well. So this kind of makes it a little bit more flexible to actually grab hold of our data. And furthermore, if you were downloading our data and wanted to have kind of on-the-fly analysis, we have implemented a bandmath tool within our API, so you can download NDVI images, NDRE, etc. I think we've got up to 7 different calculations. This tool is available within our subscriptions API and orders API. So to summarize, so I'm going kind of more into the Arctic side of things. Because of these high latitudes, we do have the ability to capture multiple captures over the high latitudes, and that also includes PlanetScope. So we sometimes with PlanetScope, because of being at the high latitude, have an afternoon pass. The Arctic coverage archives from about 2017. The best time of the year for imagery, as I mentioned, is from April to August. But there are sometimes coverages between in March and October, depending on the weather conditions. However, the remaining couple of months are limited due to the poor sun elevation. We do have limited open water coverage. This extends to about 15 to maybe 20 kilometers offshore. Open water mapping is a little trickier to do from our point of view. But this is just the next couple of slides demonstrate that the coverages mentioned beforehand. So this demonstrates the coverage from June 2017 all the way through to June 22. Obviously, June 2016, you can see there we weren't actually capturing over the high latitudes, but June 17 we started to do so, and it's kind of been increasing the entire time. So June 22 looks like we do have quite a few images. These are the good coverages in summertime. So from between March and October, you can see March we do have a number of images, and also in October, but obviously kind of June, July, August times seem to be best for captures. And finally, we want to be quite transparent here. So we want to showcase that there are very limited coverages in November, February time. So you can see January is virtually nothing, December's pretty limited, November quite limited, but then going back into that summer period, there are a lot more optical images over the high latitudes. So we do have a tool in our Planet Explorer called Story Mode, and this allows us to kind of create GIFs out of our imagery. And this is a bit of a funky one, but it does goes to show this glacial movement, but among other processes within the Svalbard and the Arctic regions. I'm not sure if Regina maybe wants to jump in here to talk about these slides.
Well, just maybe to just leave you with some overview of kind of where we are with science, because we work with scientists since the beginning, and also it's one of our key activity for business development. So just to give you an overview, that there is actually a lot of scientific papers already, including Planet data, and this rate of publication is getting higher every year. So there is around 2 publications a day right now on average. And actually cryosphere, which includes the Arctic and polar regions, is surprisingly the key topic, or let's say theme, that is covered by this publication. So we are very actually excited to work with the science community and develop it further.
And just to add to that, so approximately 75% of these papers are actually peer reviewed, and the rest are conference papers or university dissertations as well. And I think these are just a few of some examples. Over 1,200 peer-reviewed publications within our website here. So if you look in the top left-hand corner, we can obviously share this with you. But we do have a publications page within our website that you can check out what is available. And a few other examples as well. Regina, maybe you want to talk a little bit about the science program.
Yes, so you might actually, of course, when we talk about science and a commercial company like Planet is talking to you, you might wonder, okay, how to access our data and how to use it. So as I mentioned, we work with scientists since the beginning, and we have at least a few ways how to access our data for free. So it really depends on the scope and who are you from to have the possibilities, you know, to access the data. We have our Planet internal ENR program, so you can just contact us and we will see what's possible. But also there are a lot of funded programs by NASA, ESA, and the German government that allows free access to our data in a limited scope. And we treat it, of course, as basically testing our use cases and also learning about what's possible with our data. So we very much appreciate interactions with you and value that very, very high. And also just to give you some maybe spoiler or like how we imagine working in the future in the Arctic. So Planet is a very mission-driven company, and we really invest a lot in high-impact programs. One program that is a flagship for us right now relates to tropical forest. It's called NIGFI. It's together with Norwegian government and KSAT, where we opened up our data sets over the tropical regions. And in our ambition would be to choose the Arctic and boreal zone even as having the next program like this. So we are very open to discuss with anyone, you know, with governments and potential sponsors to do that, just simply to open up our data sets over the whole region for the benefit of all. And just something that, of course, needs a lot of discussions, feasibility studies before. And one small step that we would like to actually get this conversation with you closer. I hope Frida doesn't mind that I do a little bit spoiler, but we are planning with SIOS like call for proposals where we would give away the data, Planet data, to science community, just simply to just see what's possible and what would be your interest to use this data set. So I think we are just, it's 11 o'clock. So if there are any questions, of course, we are happy to answer. And thank you very much for your attention.
Thank you very much, everyone.